Hello class, we're going to walk through this independent samples t-test in class example, which is no longer in class, but still, we're going to walk through it together because that's what we would have done in the real classroom. Jamie thinks that she can improve intellectual functioning among individuals with dementia symptoms. She obtains a sample of individuals who have been diagnosed with dementia and half check in with their doctors each month, and the other half receive a supplement and check in with their doctor in order to remove beta amyloid deposit. After 3 months, she has each individual take a memory test, and we're going to use the scores below in order to decide what type of test we should use, do the alternative, and then look at to see if there's a difference. So in this case, Jamie is using that between subjects design. With the between subjects, we have two groups of individuals. They've been randomly assigned to one group or the other to either receive the supplement or to not receive the supplement, and then we are comparing between them. And so we could more explicitly say that this is an experimental design because we have that random assignment piece. So what type of test should she use? Well, it's useful that I put the name right up here, but never assume, right? Sometimes those things are not exactly as they seem. But in this case, in fact, we are going to use the independent samples t-test because we want to make a comparison between two samples that are relatively independent of each other. They were randomly assigned. Her alternative hypothesis, so Jamie thinks that she can improve, and this word is important, because by saying that she can improve it, she's indicating that one group should perform better than the other. We're going to assume that group 1 is the control and group 2 is the experimental group. The reason being that whenever I collect data, create data, I always use the control as group 1, experimental as group 2, because I do them in alphabetical order so I can remember which number is which, and C comes before E. So Jamie's alternative hypothesis is that the control group will do more poorly than the experimental group. So we can say that X bar for the experimental is going to be greater than X bar for the control group. Now we're going to look and see, is that true? Is the alternative, does the data support it? Is the data consistent with that alternative perspective? So I'm going to go over into Excel, and basically I've pulled in the data, I've reformatted it slightly so that each person is on their own row. And then just to make the video go a little bit faster, I've already typed out each of the formulas that you're going to need, and most of them are familiar to you with a little bit of a twist. So COUNTIF allows us to count A2 through A41 if it is a 1. So we're looking at the number of individuals that are in that first condition, in the control condition. So if their condition is 1, if they're in the control condition, we should count them, and we have 20 individuals in that condition. And similarly, we can then count A2 through A41 if their condition is 2, if they're in the experimental condition. So we have 20 individuals in each group. That's consistent with what we see here, where there's 20 in the first group and then also 20 in the second group. Since that's the first time we've used those formulas, it's always good to double check that they're doing what we think they're doing. The next formula is average if. So I'm going to say average if A2 through A41 is 1, then average whatever is in B2 through B41. And we find the average for the first group, the control group, is 64.6. we could double check that by saying we know what the average function does. If I average the first 20 people, all of whom are in that first group, do I get the same thing? I do in fact get that. So it looks like that function is being used properly. Similarly, we're going to average if A2 through A41 are 2. We want to average whatever's in the associated B column. And we find that the average there is 68.15. Again, we can double check that we're using that function properly since it is new. And then we find for the second 20 people who are in the experimental condition, their average is in fact 68.15. Unfortunately, I don't think there's a variance if function, so we could compute that though by just saying take the variance of this sample for the first 20 people, and if they weren't organized, we could always organize or sort by their grouping variable in order to make it as easy as it is in this case. In this case, it's already sorted for us, which makes that easy. And then we're going to get the variance for the second group of people. And once we have those two variances, then we can do the standard error of the mean. And I talked about this in the first video that I posted, but we can go and look at the formula for the standard error of the mean. And we can see that for the independent samples t-test, we're eventually going to get t obtained. So we're going to need this standard error of the mean, the SD m1 minus m2. If we look for the standard error of the mean for SD m1 minus m2, we see that we have to have variance for the first group, variance for the second group. We're going to divide both of those by n1 and n2, whatever the n is for those groups, the appropriate group. So we're going to say equals, eventually we want the square root, and first we're going to say take the variance of the first group, divide it by the n for that group, then take the variance for the second group, divide it by the appropriate n. In this case, we do have equal n's, and as I mentioned in the first video, there is a more simplistic formula, but we'll go ahead and use this one because this will always work, whether the n's are equal or whether they are not. We find that the standard error of the mean is 1.26, and then we can check our t obtained. And so our t obtained is going to be the difference between our control group and our experimental group. And then typically we would subtract the difference expected in the population. And so if you look at the formula, we see m or mu1 minus mu2. Well, if there was no difference between these individuals, especially when they started, for instance, because they're being randomly assigned, we would expect that mu1 minus mu2 would result in a difference of 0. And so assuming that that is what we're interested in, is to see is this difference something other than 0, we can simplify this formula. So we could put in the 0, we could not put in the 0, it really won't make much of a difference. But if you want to put it in there as a placeholder to remind yourself, hey, what am I doing with that mu1 minus mu2, you can go ahead and put it in there. And then we're going to divide that by the standard error of the mean. And we find that t obtained using the independent samples t-test is negative 2.81. And then to check and see if that's significant, we need to compare it to the critical value. And to get the critical value, we need degrees of freedom. The degrees of freedom for the independent samples t-test, because we have to calculate a mean for group 1 and group 2, a mean for the control group and the experimental group, is going to be the number of individuals in the first group minus 1, because we lose a degree of freedom for that first group, plus the number of individuals in the second group minus 1, because we have to calculate a mean, so we lose a degree of freedom for that group, and that gives us 38. When we scroll down and look at t critical on 38 degrees of freedom, we see that because she has a one-tailed test, so alpha is 0.05, so alpha is 0.05, it's one tailed, and there's 38 degrees of freedom, so we see that information right here in that cell. our cutoff is 1.69. And we can think about, should that be positive, should that be negative? She anticipates that the experimental group will score more highly on the memory performance than the control group. So if they did better, right, we're subtracting, when we look here, we're subtracting E4 minus E5. And in fact, E4 is the control, which we expect to do more poorly. E5 is the experimental, which we expect to do bigger. If we subtract the larger number from the smaller number, we should end up with a negative number. So this, in fact, would be negative 1.69. And importantly, if we drew out our chart, we would find that this is more extreme, this is rarer. Compared to the t-critical, it's beyond. And so because of that, it is significant. We reject the null hypothesis. Our data is consistent with the alternative hypothesis. It's consistent with the idea that Jamie presents that potentially this drug can improve intellectual functioning.